Well, I hope you appreciate that we have inducted you into some real magic. The magic of building languages, really building new languages. What have we looked at? We've looked at an Escher picture language. Right, this language invented by Peter Henderson. We looked at a digital logic language. Let's see, we've looked at the query language. And the thing you should realize is even though these were toy examples, there really are the kernels of really useful things. So for instance, the Escher picture language was taken by Henry Wu, who's a student at MIT, and developed into a real language for laying out PC boards, right, based just on extending those structures. And the digital logic language Jerry mentioned when he showed it to you was really extended to be used as the basis for a simulator that was used to design a real computer. And the query language, of course, is kind of the germ of Prolog. So we built all of these languages. They were all based on Lisp. A lot of people ask, what particular problems is Lisp good for solving for? The answer is Lisp is not good for solving any particular problems. What Lisp is good for is constructing within it the right language to solve the problems you want to solve. And that's how you should think about it. So all of these languages were based on Lisp. Now what's Lisp based on? Where's that come from? Well, we looked at that too. We looked at the metacircular evaluator. The metacircular evaluator, and sort of said, well, Lisp is based on Lisp. And when we started looking at that, we got into some real magic, right? So what does that mean, right? Y operators and fixed points, and the idea that what this means is that Lisp is somehow the fixed point equation for this funny set of things which are defined in terms of themselves. That was sort of real magic. Well, today, for our final piece of magic, we're going to make all the magic go away. We already know how to do that. The idea is we're going to take the register machine architecture and show how to implement Lisp on terms of that. And remember, the idea of the register machine is that there's a fixed and finite part of the machine. There's a finite state controller, which does some particular thing with a particular amount of hardware. There are particular data paths, the operation the machine does. And then in order to implement recursion and sustain the illusion of infinity, there's some large amount of memory, which is the stack. So if we implement Lisp in terms of a register machine, then everything ought to become, at this point, completely concrete. All the magic should go away. And by the end of this talk, I want you to get the feeling that as opposed to this very mysterious metacircular evaluator, that a Lisp evaluator really is something that's concrete enough that you can hold in the palm of your hand. You should be able to imagine holding a Lisp interpreter there. All right, how are we going to do this? We already have all the ingredients. See, what you learned last time from Jerry is how to take any particular couple of Lisp procedures and hand translate them into something that runs on a register machine. So to implement all of Lisp on a register machine, all we have to do is take the particular procedures that are the metacircular evaluator and hand translate them for a register machine. And that does all of Lisp. Right, so in principle, we already know how to do this. And indeed, it's going to be no different in kind from translating, say, recursive factorial or recursive Fibonacci. It's just bigger, and there's more of it. So it'll just be more details, but nothing really conceptually new. Right, also, when we've done that, and the thing is completely explicit, and we see how to implement Lisp in terms of actual sequential register operations, that's going to be our final, most explicit model of Lisp in this course. And remember, that's a progression through this course. We started out with substitution, which is sort of like algebra. And then we went to the environment model, which talked about the actual frames and how they got linked together. And then we made that more concrete in the metacircular evaluator. There are things the metacircular evaluator doesn't tell us. And you should realize that. For instance, it left unanswered the question of how a procedure like recursive factorial here somehow takes space that grows. On the other hand, a procedure which also looks syntactically recursive, called fact-iter, somehow doesn't take space. We justified that it doesn't need to take space by showing the substitution model, but we didn't really say, how it happens that the machine manages to do that. Right? That has to do with the details of how arguments are passed to procedures. And that's the thing we didn't see in the metacircular evaluator, precisely because the way arguments got passed to procedures in this Lisp depended on the way arguments got passed to procedures in this Lisp. Right? But now that's going to become extremely explicit. Okay. Well, before going on to the evaluator, let me just give you a sense of what a whole Lisp system looks like. So you can see the parts we're going to talk about and the parts we're not going to talk about. Let's see, over here is a happy Lisp user. And the Lisp user is talking to something called the reader. The reader's job in life is to take characters from the user and turn them into data structures in something called a list structure memory. Right, so the reader is going to take symbols, parentheses, and A's and B's and 1s and 3s that you type in and turn these into actual list structure, pairs and pointers and things. So by the time the evaluator is going, there are no characters in the world. And of course, in more modern Lisp systems, there's sort of a big morass here that might sit between the user and the reader. Window systems and top levels and mice and all kinds of things. But conceptually, characters are coming in. All right, the reader transforms these into pointers, right? Pointers to stuff in this memory. And that's what the evaluator sees. Okay. The evaluator has a bunch of helpers. It has all possible primitive operators you might want. So there's a completely separate box. The floating point unit, or all sorts of things which do the primitive operators. And if you want more special primitives, you build more primitive operators, but they're separate from the evaluator. The evaluator finally gets an answer and communicates that to the printer. And now the printer's job in life is to take this list structure coming from the evaluator and turn it back into characters. And communicate them to the user through whatever interface there is. Okay. Well, today, what we're going to talk about is this evaluator. The primitive operators have nothing particular to do with Lisp. They're however you like to implement primitive operations. The reader and printer are actually complicated, but we're not going to talk about them. They sort of have to do with details of how you might build up list structure from characters. So that is a long story, but we're not going to talk about it. The list structure memory we'll talk about next time. So pretty much except for the details of reading and printing, the only mystery that's going to be left after you see the evaluator is how you build list structure on conventional memories. But we'll worry about that next time, too. Okay. Well, let's start talking about the evaluator. The one that we're going to show you, of course, is not I think nothing special about it. It's just a particular register machine that runs Lisp, and it has 7 registers. And here are the 7 registers. There's a register called exp, and its job is to hold the expression to be evaluated. And by that I mean it's going to hold a pointer to some place in list structure memory that holds the expression to be evaluated. There's a register called end, which holds the environment in which this expression is to be evaluated. And again, I mean a pointer. The environment is some data structure. There's a register called fun, which will hold the procedure to be applied when you go to apply a procedure. A register called argle, which holds the list of evaluated arguments. What you can start seeing here is the basic structure of the evaluator. Remember how evaluators work. There's a piece that takes expressions and environments, and there's a piece that takes functions or procedures and arguments. And going back and forth around here is the eval-apply loop. So those are the basic pieces of eval and apply. Then there's some other things. There's continue. You just saw before how the continue register is used to implement recursion in stack discipline. There's a register that's going to hold the result of some evaluation. And then besides that, there's one temporary register called unev, which typically in the evaluator is going to be used to hold temporary pieces of the expression you're working on which you haven't gotten around to evaluate yet. All right, so there's our machine, a 7-register machine. And of course, you might want to make a machine with a lot more registers to get better performance, but this is just a tiny minimal one. Well, how about the data paths? This machine has a lot of special operations for Lisp. So here's some typical data paths. Typical one might be, assign to the val register the contents of the exp register. That's, in terms of those diagrams you saw, that's a little button on some arrow. Here's a more complicated one. It says branch if the thing in the expression register is a conditional to some label here called the EV conditional. And you can imagine this implemented in a lot of different ways. You might imagine this conditional test as a special purpose subroutine. And conditional might be represented as some data abstraction that you don't care about at this level of detail. So that might be done as a subroutine. This might be a machine with hardware types, and conditional might be testing some bits for a particular code. Right, all sorts of ways. That's beneath the level of abstraction we're looking at. Another kind of operation, and there are a lot of different operations, assign to exp the first clause of what's in exp. This might be part of processing a conditional. And again, first clause is some selector whose details we don't care about, and you can, again, imagine that as a subroutine which will do some list operations, or you can imagine that as something that's built directly into hardware. The reason I keep saying you can imagine it built directly into hardware is even though there are a lot of operations, there's still a fixed number of them. Forget how many, maybe 150. So it's plausible to think of building these directly into hardware. Here's a more complicated one. You can see this has to do with looking up the values of variables. It says assign to the val register the result of looking up the variable value of some particular expression, which in this case is supposed to be a variable, in some environment. And this will be some operation that searches through the environment structure however it is represented and goes and looks up that variable. And again, that's below the level of detail that we're thinking about. This has to do with the details of the data structures for representing environments. But anyway, there is this fixed and finite number of operations in the register machine. Well, what's its overall structure? Those are some typical operations. Remember what we have to do. We have to take the metacircular evaluator, and here's a piece of the metacircular evaluator. This is the one using abstract syntax that's in the book. It's a little bit different from the one that Jerry showed you. And the main thing to remember about the evaluator is that it's doing some sort of case analysis on the kinds of expressions. So if it's either self-evaluating or quoted or whatever else. And then in the general case where the expression that's looking at is an application, there's some tricky recursions going on. First of all, eval has to call itself both to evaluate the operator and to evaluate all the operands. So there's this sort of red recursion. Eval is walking down the tree. That's sort of the easy recursion. That's just eval walking down this tree of expressions. Then in the evaluator, there's a hard recursion. There's eval, the red to green. Eval calls apply. That's the case where evaluating a procedure argument reduces to applying the procedure to the list of arguments. And then apply comes over here. Apply takes a procedure and arguments, and in the general case where there's a compound procedure, apply goes around and green calls red. Apply comes around and calls eval again. Eval is the body of the procedure in the result of extending the environment with the parameters of the procedure by binding the arguments. Except in the primitive case where it just calls something else primitive apply, which is not really the business of the evaluator. So this sort of red to green, right, that's the eval apply loop, and that's the thing that we're going to want to see in the evaluator. All right, well, it won't surprise you at all that the two big pieces of this evaluator correspond to eval and apply. There's a piece called eval dispatch and a piece called apply dispatch. And before we get into the details of the code, the way to understand this is to think, again, in terms of these pieces of the evaluator having contracts with the rest of the world. You know, what do they sort of do from the outside before getting into the grungy details? Well, the contract for eval dispatch, remember, it corresponds to eval. It's got to evaluate an expression in an environment. So in particular, what this one is going to do, eval dispatch will assume that when you call it, that the expression you want to evaluate is in the exp register. The environment in which you want the evaluation to take place is in the env register, and continue tells you the place where the machine should go next when the evaluation is done. Eval's dispatch's contract is that it'll actually perform that evaluation, and at the end of which it'll end up at the place specified by continue. The result of the evaluation will be in the val register, and just warns you that it makes no promises about what happens to the rest registers. All other registers might be destroyed. So there's one piece. Okay. The other big piece is apply dispatch that corresponds to apply. It's got to apply a procedure to some arguments. So it assumes that this register argle contains a list of the evaluated arguments. Fun contains the procedure. Those correspond to the arguments to the apply procedure in the metacircular evaluator. And apply in this particular evaluator, we're going to use a discipline